Hello everyone, this is Kim from the University of Melbourne, and welcome to this demonstration of a multi-agent incident response system. This is the main entry point of the system where the security operator can log in. Now, before I walk through the functionality, let me start by briefly discussing the architecture. So this is a multi-agent system that consists of many LLM-based agents that work collectively and autonomously to investigate a security incident and generate a response plan. To achieve this, the agents can invoke various tools. For example, they can use threat intelligence APIs to retrieve relevant information to the incident. So as an example, the agents could search for Samba cry to fetch detailed information about that particular vulnerability and related attacks. In addition to the threat intelligence APIs and knowledge bases that we see here, the agents also have access to a digital twin, namely a virtual replica of the system that was affected by the incident. So as an example, here we have a cloud-based infrastructure, and to deploy a digital twin of this infrastructure, we simply click on this button here. And what happens behind the scenes is that it then takes the containers and virtual machines from the cloud environment and deploys them in a virtual network. And that virtual network then provides a safe environment where the agents can access the terminal and they can run commands in order to investigate the incident and look for signs of compromise. Now, in addition to the digital twin, the agents also have access to a Python sandbox where they can execute arbitrary Python code. And this allows the agents to run high-performance planning algorithms in order to compute effective response actions. The main interface for the security operator that is using the system is this page that we see here. So here they can provide details about their system, they can provide evidence about the incident in the form of security alerts, and they can specify constraints. Now, for the purpose of the demonstration, I prepared an example incident that we can load. And before the operator starts the agentic investigation and response to this incident, it can configure the system by going to this page here and specifying which tools and which agents should be enabled. They can also specify for each agent which particular LLM should be used. And once the operator has configured all of these settings, it can then start the agentic investigation by clicking on this button down here. And while the system is running, it can monitor the progress of the agents through this activity log that we see here, which provides detailed information in real time about the different steps that the system is going through. The first step, as we see in the log right now, is that the system is invoking an agent called the reporter agent, which is responsible for assessing the scope of the incident and generating an incident report. So we can see right now that the agent has started and has already started the investigation by executing commands on a digital twin. And right now it is running 3 sub-agents in parallel, or actually 5 agents in parallel, that are investigating specific hosts of the system by executing various commands on the digital twin and looking for log files and reasoning about the different evidence that they can find inside of the digital twin. So the system has now terminated, and we can do a brief analysis of the activity log to inspect the results and track the progress. The first step was to invoke an agent responsible for assessing the incident and generating an incident report. And that report can be seen here. So we have a summary of the incident, an attack vector analysis, indicators of compromise, affected assets, and the agent also generated an image to illustrate the conjectured attack path, as you can see in the figure here. The system then used this generated report and passed it on to a verifier agent responsible for validating the report against the digital twin. And the outcome of that agent is shown here. So it finds that the report is largely correct, but there are a few points that need to be addressed for factual accuracy. And after addressing these points and revising the report, the system then moved on to invoke another agent responsible for validating the conjectured attack path from the attacker's point of view. So essentially performing a white box penetration test against the digital twin to test if the conjectured attack path is actually feasible. And you can see the outcome of that test here, which shows that the attack path is fully validated. And here are the exact commands for reproducing the attack according to the agent. So this concludes the investigation part of the response. And now the system will move on to the second phase, which is about recovery planning. So planning for how to recover the system from the incident in the most effective way. And the first step of that phase is to invoke an agent responsible for generating a code model of the recovery process. And the outcome of that agent is shown here. So it generates essentially a Markov decision process implemented as Python code of the recovery process, which can be used for what-if analysis and for enabling efficient recovery planning, where we can test out different ways of recovering the system and compare the operational cost involved with different recovery actions. So here in the table here, you can see the list of actions, where each action is associated with certain commands to run on the system and also have an intended effect. And here you can download the code model as a Python script. The system then took that code model and passed it on to a verifier agent responsible for making sure that the code model is actually aligned with the digital twin. And the outcome of that agent is shown here. So it finds that the model is functional and largely correct, but there are a few points that can be improved as listed here. And after revising the code model based on this feedback, the system then moved on to invoke the planner agent, which was responsible for using the code model to compute a strategy or a policy for recovery. And the agent was free to use different methods for doing this computation, but in this particular instance, it chose to use reinforcement learning. And here you can see the convergence curve when optimizing the recovery strategy. It also generated a report to summarize the strategy as listed here, where you can see the recommended action sequence, so sequence of actions for containing the attack and effectively recovering the system while minimizing operational cost and making sure that all operational constraints of the system are satisfied. Finally, the system moved on to take that code recovery policy and pass it on to a different agent that was responsible for validating the policy on the digital twin. So essentially testing all of the actions in the recovery plan and comparing their outcomes with their expected outcomes in the code model. And here you can see the results. So it finds that most of the actions are validated correctly, but there are a few actions that have some mismatch between what was the expected outcome. And finally, after revising the policy based on that feedback, the orchestrator agent then takes all of these outputs from all of the different agents, so the incident report, the penetration testing report, the code model, and the response plan, and aggregates all of that into a final comprehensive report that can be used as decision support for a security operator. And that report is shown here. Now, in the end of this report, there's also some execution statistics over that quantifies how the system performed. So we can see that it operated for around 40 minutes. And in this table here, you can see also a breakdown per agent and per tool call of how many tokens were used, how many function calls were used, and how much time was spent by each agent.